Now let's take a look at an interesting case when some of the elements in the permutation or combination problems are repeated elements. Remember that when we found a number of permutations of n objects taken r at a time, we assumed that those n objects were all distinct. And so that was what we saw in the previous case. Now let's consider the case where we do have elements that are the same. Here's an example. How many arrangements of the letter of the word egg are there? Now notice that arrangements here would be switching the letters and getting different uh, arrangements or permutations of those letters. But notice that there are two G's in the word. So when you swap those two G's, you have the same thing. So you don't have a different permutation. So how do we handle that type of problem? Well, there is a way to do that, and it's to relate that to the regular permutation that we learned before. So let's suppose that the two letter G's that we see in the word egg, they are distinct letters. For that, we're going to say that one of those G's is G1 and the other G is G2. So we're going to make them distinct. Now, if in this case, the three letters now are distinct. So we have E, G1, G2. What is the number of arrangements or permutations of those three letters when you take those three at a time? So that's P3, 3. That gives us 6. Now let's list all of those arrangements or permutations. And then here we're going to see a relation between that and what we want when the letters are the same. The two G's are the same. So here are all the permutations. So it's E, G1, G2. Here's another E, G2, G1, G1, E, G2. So we have a total of 6 arrangements or permutations. Now notice that these two arrangements here, they actually come from the same arrangement when we consider the two G's to be exactly the same. Right, so the EGG, that permutation or that arrangement yields 2 when we make those two G's distinct. And same thing here, these two arrangements, G1EG2 and G2EG1, both of them come from this same arrangement on this side. And on this side is when we have the original question. We want to know how many arrangements of the letters of the word egg are there. And we can see here that there are 3 of them, EGG, GEG, and GGE. And each one of those yield or produces 2 permutations or arrangements when we make those repeated letters distinct. And that's a relation that we can, from that relation, we obtain a formula. If we had 3 letters that were exactly the same, let's suppose we have the letters E, G, 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 3 G's instead of 2 G's, then those 3 G's would yield 3 factorial new permutations if we make those G's distinct. And that's the relation, is the 2 factorial. And if we had 3 repeated letters, then it would be 3 factorial. If we had 4 identical letters, then those each permutation here, each arrangement would yield 4 factorial on this side. And that is a relation. That is the relation between P33 and the number of arrangements or permutations of 3 objects out of 3 with 2 elements that are repeated. Each permutation from P generates 2 factorial permutations that are included in P33. So that is the relation. P3, 3 is P times 2 factorial. So notice once again we have this idea of eliminating the repetition. So P33 is when we consider all letters to be distinct. But if two of them are identical, then in order to get rid of that of the order of those two letters, then we divide it by 2 factorial. So it's the kind of a similar idea that we've seen before with the combination, the relation between combinations and permutations. Now this is not combination. This is permutations or arrangements of repeated objects. And we can actually extend this to any number of letters that are repeated or objects that are repeated. This is theorem 8.7 in the textbook. And to summarize the theorem, this is basically saying that if you have n objects and there are groups of objects that are identical, so n1 of them are identical, n2 of them are identical. So you have groups of objects that are repeated from those n objects. Then the number of permutations or arrangements will simply be n factorial, and we divide by the number of objects in each repeated group, in each group of repeated objects. Just as an analogy here, let's say you have 100 types of fruits. Let's say 20 of those fruits are bananas, 30 are apples, and let's say 10 of them are grapes. So in order to arrange all those fruits on a shelf, for example, on a stand, and you put them in order, but some of those fruits are repeated. In order to not count those arrangements twice, we have to get rid of the repetition by dividing by n1 factorial. So it's a number of apples factorial. And then here will be number of bananas factorial, and so forth. And here is an example. How many distinct arrangements of the letters in the word economic are there? So the word economic has 8 letters, but some of them are repeated. As you can see, there are 2 O's and there are 2 C's. So we can find the number of arrangements by doing 8 factorial. So you basically start the problem by considering all of these letters to be distinct. So this would be E, this is C1, and this is C2, this is O1, this is O2. So consider all of them to be distinct. So when you arrange the letters, you're actually picking 8 of those letters out of 8, and you're arranging them. So that will be 8 factorial. Now, some of the letters are repeated, so there are 2 C's, so we need to divide by 2 factorial. But also, there are 2 O's, so we divide again by 2 factorial. And that gives us 8 times 7 times 6, 5, 4, 3, 2, 1. So 2 factorial, 2 factorial. 2 factorial is 2, 2 factorial is 2. That's 4. That will cancel with that. multiplying these numbers according to my calculations here, it would be 10,080 of arrangements. Now, I want to go back here to Theorem 8.7 and also mention that in the book, um, you will see another way of writing this formula using combinations. And so this can be written as C. It seems like it's more complicated. It's Cn, comma n1 times Cn minus n1, comma n2, Cn minus 1, n minus n1, and minus n2, comma n3, and this is all the way down to combination n minus n1 minus n2 minus n k minus 1, comma nk. Let me explain how this works. When you have objects that are repeated, you can think of arrangements by actually grabbing those objects that are repeated and selecting them because they are repeated anyway, so the order is not important. So out of those n objects, you're picking the first group. You're picking any, you can pick any group, but let's say you pick the first group of repeated objects. Let's say you have n1 apples, okay? So you select n1 slots, right, for your apples. And in those slots, the order doesn't matter. So you select them and you arrange them without order. So that's called combination, right? So out of those n objects, you pick n1 slots, right? So you can put your apples. Then the next part would be grabbing another group, let's say bananas now, and there are n2 of them. So out of those remaining objects, then you pick n2 for the bananas. That's why you have the total number of objects minus the number of elements in the first group. And you selecting n2 objects for that second group. And then the remaining objects, which would be the remaining slots, would be n minus n1 minus n2. So you're going to pick n3 of those remaining for your next group. Let's take a look at one example and see how that works. Well, we can actually use the same example here. So we can look at the word economic, and there are 8 letters. Some of the letters are repeated. So let's start with the letter E let's start with the letter C, since there are 2 of them. So out of those 8 slots or 8 positions of the letter, I'm going to select 2 of those for the C's because there are 2 of them. So out of 8, I select 2 of them so I can store the C's. So you're picking 2 slots out of the 8. Then next, let's look at another repeated object with the letter O. So from the remaining slots, which is now 6 because you already picked 2 slots, you're gonna, out of those 6, you select 2 slots for your letter O. And the remaining slots let's look at letter E, for example. There's only one letter E. So out of the remaining slots, which is 4, right, we pick 2 slots here for that. Then the remaining number of slots is 6. Now we pick 2 for the letter O. The remaining number of slots is 4. Now we're going to pick 1 out of those 4 for the letter E, because there's only one letter E. Now the remaining number of slots is 3, and we pick out of those 3, we pick 1 for the letter N. Now the remaining number of slots is 2. We're going to pick 1 for the letter M. And finally, out of the remaining slots, which is only 1, we're going to pick out of those 1 remaining slots, we're going to pick 1 slot for the letter I. And that's the and that's another way of getting the number arrangements. Now I want to mention here that this is exactly what this is saying. So it's the total number of objects is 8. Here's N, and then here's the first group of repeated letters or objects. The number of that is those objects is 2. Then here it's 6 because it's N minus the number of elements in the first group. So that's why it's 6 here. And then the number of elements in the second group. And then here is the number of total elements minus the number of elements in the first group minus the number of elements in the second group. That's why I have 4, because it's 8 minus a 2 minus a 2, that gives us 4. So that's one observation. And it turns out that this is the same as this one. Let me show you why. And it's very easy to see. It doesn't look like, but it is. Remember how we find combination 8, 2? 2 slots, that's 8 times 7, and that's divided by 2 factorial. That's this part. And here is 6 times 5, because the total number of objects here is 6, and you have 2 slots. See, that's why it's important to recall that the number of combinations comes from the number of permutations, or 2 factorial. So this is divided by 2 factorial. Here, that's 4, and it's only 1, so divided by 1 factorial. Here, it's 3, because it's only 1 factor, divided by 1 factorial. Here is 2, divided by 1 factorial. Here is 1, divided by 1 factorial. As you can see, this is exactly what you see right there. It's 8 factorial, because it's 8 times 7 times 6, 5, 4, 3, 2, 1, divided by 2 factorial times 2 factorial. Well, we don't put 1 factorial. 1 factorial is 1, so a factor of 1 doesn't influence anything. That's why you don't see that in here. So it's exactly the same answer.